Good morning, class. In our previous class, we discussed about acid-base reactions and Ka values. Today, let's discuss about pKa values. Now, this pKa is one universal number which can determine the relative strength of an acid or a base. So, we can determine the relative acidity or basicity of an acid or a base. So, let's see how. Let's discuss pKa values by taking some examples. HCl. HCl dissociates spontaneously to hydrogen and chloride. This is a reversible reaction. Writing the dissociation constant of this acid, it is found as 10 raised to the power 8. Of course, this value is found or calculated experimentally. Just by looking at the reaction, you cannot figure out its Ka value, right? Let's take one more sample reaction. Sample reaction of water. Again, this is a reversible reaction giving H ion and OH ion. The dissociation constant of this reaction, basically the dissociation constant of this acid is found to be around 10 raised to the power 15 experimentally. Let's take one more sample reaction. Sample reaction of methane. Again giving a proton, hydrogen ion and methyl group. Now this reaction is not exactly taking place because it is a very unfavorable reaction. I am just writing it down to devise the pKa values. Now the dissociation constant of methane is 10 raised to the power minus 50. 10 raised to the power minus 50. Now this is, we know, is a stronger acid. And this is the weakest of all. This is a weaker acid. Clear? So by looking at these values, we can figure out higher the value of Ka, stronger is the acid. Lower is the value of Ka, weaker is the acid. Right? Now, to deal with these negative exponents is very inconvenient. So to make this convenient, let's take log of these values. Log of Ka. So log 10 raised to the power 8 will become 8. Log of this will become minus 15. And log of 10 raised to the power minus 50 will become minus 50. Now, in organic chemistry, the most of the acids we deal with are weak acids, which means we will have to deal with these negative values more often. So again, to make this more convenient and handy, a new thing was devised known as pKa. pKa values were devised. pKa is defined as the negative log of Ka values. So, taking negative log of this becomes minus 8. Taking negative log of this makes it 15. And this becomes 50. So, now you know, lesser the value of pK, stronger is the acid. Higher the value of pKa and weaker is the acid. So, now we can conclude, higher the value of Ka, stronger is the acid. And lesser is the value of pKa. Similarly, lower the value of Ka, weaker is the acid, and higher is the value for pKa. Now the pKa values of all the acids, they are tabulated in a table form, and this table is known as a pKa table. And this table is very useful in organic chemistry. So let's see how this table can be used. So here I have drawn a very small portion of a pKa table. Now, just by looking at the pKa values, we can determine or we can identify the relative strength of acids and bases. These pKa values are of great importance in organic chemistry. By using these pKa values, we can also determine whether an acid-base reaction will proceed or not, whether it is a favorable reaction or not. Now, just by looking at the pKa values, we can identify that HCl is the stronger acid of all. Why? Because we just now discussed, lower the value of pK, stronger is the acid. Higher the value of pK, weaker is the acid, right? So in this table at the bottom, we have the weaker or the weakest acid, and at the top we have the stronger acid. So this means down the table, acidity of the acids decreases. At the same time, let's take a look on the conjugate base. Lesser is the value of pKa, weaker is the base. Always remember. So on top we have the weakest base, WB I am writing, and at the bottom we have the stronger base. We have the stronger base. This means on moving down the table, the basicity of the conjugate base increases. So this is to be remembered. This is a point to be kept in mind always. In the pKa table, as we move down the table, the acidity decreases and the basicity increases. Now, let's see how these pKa values can be used to determine whether an acid-base reaction is favorable or not. Let's take the first example I am taking is CH3 when reacts with ammonia gives CH4 plus NH2. Now the first step is to identify which is our conjugate acid, which is conjugate base, and which is our acid and base. I am abbreviating acid by A, base by B, conjugate base by CB, and conjugate acid by CA. So in this reaction, since ammonia is donating a proton, so this is our acid, and CH3 is accepting the proton, therefore CH3 is our base, right? Now ammonia after donating a proton becomes NH2, therefore this is our conjugate base, because by definition we already know that an acid after donating a proton becomes a conjugate base of that acid, right? Similarly, CH3 base after receiving this proton, accepting this proton becomes CH4. So therefore this is our conjugate acid. Clear? Second step is to find out by using this table which one is a stronger acid and which one is a weaker acid, and for base also. So out of these two, ammonia and methane, just take a look on the table. Ammonia is above methane, right? So methane is a weaker acid. So I am writing here WA, weaker acid. And ammonia is a strong acid. So I am writing SA. Are you getting the point? Out of CH3 and NH2, NH2 is above CH3. So CH3 is the stronger base. So I am writing SB for stronger base and WB for for weaker base. Clear? Now comes the third step. Third step is the thumb rule to be kept in mind always. The third rule is that a strong acid and a strong base, a strong acid on a strong base gives a weak acid and a weak base. Then only the reaction will be favorable. So look at this reaction. In this given reaction, strong base and strong acid, they are giving a weak acid and a weak base. So on this basis, we can conclude that this reaction is a favorable reaction. This reaction will proceed. So that's all in today's class. We'll continue in our next class. Thank you.